Hi, my name is Ada, and I would like to tell you about the simulations of the telescope test structure, which will be used for dimensional stability test of the LISA telescopes that will be run at the University of Florida. The LISA telescope will be used to send and receive light between the LISA spacecraft. Therefore, it is a part of the science interferometer, and as a consequence, subject to 1 picometer per root hertz stability requirement, micrometer stability requirement over the entire mission duration, and sub-ppb backscatter light requirement into scientific beam path. The telescope for LISA mission will be delivered by NASA, and the telescope prototypes will be tested for those requirements at the University of Florida. If you are interested in knowing more about plans and preparations done by our group, I recommend PEP Sanjuan stock, which is an overview of all the telescope-related activities in our group, and Soham Kulkarni's stock about development and tests currently being performed on the telescope test structure. Now I will concentrate on simulation framework, which is being developed to simulate optical properties of the telescope testbed. Let me start with the stability measurement concept. The telescope picometer and micrometer lens stability measurements will be performed by placing the telescope prototype in the rigid testbed made out of ultra-low thermal expansion glass. Figure on the top shows model of the telescope test structure, or TTS, with NASA telescope design placed inside. The test structure supports optical cavity mirrors, thus form optical cavity around the telescope. This cavity, together with a stable reference cavity, is placed inside the thermally controlled vacuum tank. Two 1064 nanometer lasers are locked individually to those two cavities. Thus, the frequency of each laser will follow its respective cavity length change. The measured signal is a difference frequency between those two lasers. The changes to this difference frequency are proportional to the length change of the telescope. Schematic of the experiment is shown in the bottom figure, and the experimental details are explained by Soham in his talk. The key part of this measurement method is to form a stable optical cavity around the telescope prototype and make sure that any noise contribution from the TTS itself stays below the LISA requirement. Here, the main goal is to develop framework for optical cavity with the LISA telescope simulations, and we want to use this framework to find a set of optical cavity parameters like radius of curvature of the cavity mirrors, required clear aperture for the cavity mirrors, and TTS length to form a stable optical cavity around the telescope. Then we would like to know the resulting Gaussian beam parameters like wave size and position, free spectral range of the cavity, mode spacing, and beam radius on telescope and cavity mirrors. Once we have those parameters, we would like to establish alignment tolerances for the TTS itself, like the parallelism of the end plates which support cavity mirrors, learn about potential misalignments during the stability measurements, and potential tune-to-length noise contributions. The final goal is to establish alignment procedure that would help us align the telescope to the telescope structure and run the measurement. The main tool used for these simulations is Optical. It is a beam tracing package which also allows for iterative solving of the cavity eigenmodes. We also use Python code to optimize multiple simulations and use it to write scripts for data analysis. Our simulations are using NASA's LISA 725 version 7A telescope design to develop and test our simulation framework. Let's look at the schematic of the telescope optical layout used for the simulations. M1 is a large, approximately 360 mm diameter parabolic mirror that collimates outgoing beam. Hyperbolic M2 plays role of a beam expander. The M1 and M2 system gives magnification of approximately 134. M3 is used to correct for beam astigmatism, thus it is a biconic mirror. M4, here flat, plays role of a returning mirror. We start our simulations with finding initial cavity parameters that give a stable cavity. The visualization of the optical cavity and the telescope simulation frame is present on the top right of the slide. Cavity mirror 2 or CM2 is placed close to the M3 mirror to reduce size of the TTS, thus the cavity mirror has to be convex, as it is placed behind the telescope people. The beam waist will be located behind the CM2. Cavity mirror 1 or CM1 is placed close to M1 telescope mirror. The initial simulations show that the radius of curvature of CM1 should be larger than 1.5 kilometers to form a stable cavity, which is shown on the graph in the bottom right corner. The red shaded region indicates waist smaller than 100 micrometers. Position of the CM1 is not critical for the cavity stability, so the mirror itself can be moved closer to M1 to further reduce the size of the TTS. We just have to keep in mind that there is no beam clipping between M2 and M1. We define initial CM1 parameters. Now we can have a look at the CM2 mirror and the possible solutions. Table here is an example of the beam and cavity parameters for a stable cavity formed around the telescope. I would like to point out that there are various stable solutions for different CM2 radius of curvature and positions, which is shown on the graph on the right-hand side. They show beam ways and transversal mode spacing dependence on CM2 radius of curvature and its position in respect to the telescope's small peephole. Those results give us confidence that we can close the cavity around the telescope. Now, I would like to talk a little bit about the cavity misalignment and alignment tolerances. To determine the alignment tolerances, we would like to know the amount of displacement of the laser beam on each telescope and cavity mirror that will be produced due to the tilt of the cavity mirrors. The schematic shows how the optical axis, which is drawn as dark dashed lines, shifts with respect to the telescope axis, indicated with dashed pink lines, and the resulting beam movement on each mirror in the system. It requires 4 microradians of the CM1 tilt to shift the beam by 10% of its size on CM2, M3, and M4, and 8 microradians tilt to shift the beam by 10% of its size on M2, M1, and CM1. Those numbers look much better for CM2 mirror, which is approximately 280 microradians for respective shifts of the beam. This is not surprising result when we think about the large beam magnification due to the presence of a telescope. Therefore, the telescope will have to be aligned to CM1 mirror, and we need to set requirements on the precision and range of the telescope to TTS alignment. To set those requirements, we need to investigate more the behavior of the optical axis inside the cavity caused by simultaneous tilt of the CM1 and CM2 mirrors, as well as possible alignment correction caused by lateral displacement of CM2. The top figure shows behavior of the optical axis if both end plates are tilted inwards. The negative tilt of CM1 is to some degree compensated by CM2 positive tilt, and the beam is hitting M2, M1, and CM1 at its center. However, there is still relatively large displacement on M3, M4, and CM2 itself. Similar situation can be observed when laterally shifting CM2. This is likely the way tilts of CM1 can be compensated to some degree. Again, this requires further investigation on the constraints for realignment of the telescope to match cavity mirror 1. The simulation framework also allowed us to investigate potential misalignment caused by the gravitational forces. Here, the unsupported telescope arm is sagging due to the gravitational force applied in a perpendicular direction, causing lateral shift of M2 and changes in the alignment conditions. Therefore, right positioning and support of the telescope during the lens stability measurement might be important to reduce potential lens-noise coupling caused by mechanical vibrations. Summarizing my presentation, we are developing framework for optical cavity built around the telescope simulations. The combination of the AutoCAD and Python codes together with the telescope optical layout provided by NASA allowed us to find set of stable cavity parameters, and as a result reduce the size of a TTS. The current size-down model of the TTS is shown on the right top corner. The next steps are towards establishing alignment tolerances of the structure itself, the range of the telescope to cavity alignment, simulation of the potential noise coupling during the measurement, and establishing the alignment procedure. Thank you for your attention.